Hello everyone and welcome to the presentation of my honors project, which is designing and testing a computer tomography of chemiluminescence setup. The objective is to, of course, design and test a CTC setup using a V-shaped flame, and also to investigate the effect of changing image resolution and the number of views in the reconstructions. So what is chemiluminescence? It is the event in which a molecule excited due to a chemical reaction emits radiation while returning to its ground state. Here to the right, you can see a figure which shows the chemiluminescence spectrum for a methane flame. So for this project, we're going to focus on the C2 radical, which can be shown here. This is the part of the spectrum that we would like to capture. However, we don't have a filter for this type of radical specifically, but there is one for the CH radical. So what will be done, and what has been done, is that we use the filter to filter out the CH radical emissions, and then we keep everything except the CH radical emissions, which means that the most prominent part of the spectrum is the C2 radical, which we want to focus on. So computed tomography basically consists on from a 2D image taking a number of projections from different views using different angles and using a discrete domain where the 3D space is divided in a number of discrete voxels. It is possible to reconstruct using line integrals basically to define what the intensity of the light for the flame in each one of these voxels is. So the design of the setup. Here you have a photo of the setup in the lab. So we have a camera, two lenses, the burner, and the filter, which was mentioned before. Here is a diagram for a more clear view of the setup, and also a bit of a zoom into the burner, so you can see here that a metal rod is used in order to create the V-shaped flame. So for the results of the reconstruction, what I'm going to do is I'm going to show the horizontal cuts of the reconstruction at a number of different heights. At 0.3, the geometry of the flame is quite simple, and therefore there aren't many noticeable differences regarding different number of views and different number of pixels. All the reconstructions are very similar. Here we can start seeing some differences between the reconstructions, and we can also start seeing some deformities in the reconstruction, especially in the shape of these lines of light, which of course are not real accurate representations of the actual geometry of a flame. Finally, the height of 0.8, the V shape of the flame can be noticed as two big points of higher intensity can be identified. However, this is only true for the reconstructions with a higher number of views. For the reconstruction with a low number of views, this can't really be noticed. For quantifying the error, what was done is that one of the original images, which is shown here, was reconstructed using basically a number of different layers basically making the reconstruction at all the possible layers, and then from subtracting the two images, the error, the total error was computed as shown in the image to the right. And as can be seen, the error in some parts of the flame is quite noticeable, and this is partly due to errors in the setup, which could have changed the geometry of the flame from picture to picture. As a conclusion, the results of the setup have been fairly convincing. However, there are some areas to improve, both in the design of the setup in order to reduce human error during the data collection, and also in the algorithm, which could use some fine-tuning in order to obtain more realistic flame geometries. Before ending the presentation, I want to thank Dr. Alexis Bolling, Leonardo Castellanos, and Dimitri Kliukin, because without their help, it wouldn't have been possible to create this project. So yeah, thanks a lot for your attention, and I hope you enjoyed the presentation.